Hi, everyone, and welcome back. So, we're going to be talking today about the concept of expected value, which has come up in the reading in chapter 11. So, basically, expected value is this mathematical tool for trying to summarize the expected outcome of a process that has a random element to it. Now, of course, if a process is random, we're not going to be able to fully capture what's going on with it just from a single number. But it's a tool that helps us to understand a little bit. So one way to think about it would be like this. The expected value tells us something about what would happen with this process, this random process, on average if we did it a bunch of times. So if I ran the process a bunch of times and averaged the result, what would the average be? What is the expected average value, right? So that's the expected value. That's the thing that we're talking about. All right, so for example, suppose that I flipped a coin 100 times. I don't know why I didn't say times. I'll go times. We flip a fair coin 100 times and count the number of heads that come up. What's the expected value? What is the expected number of heads you get? And we know, because we've talked about these things a lot of times before, we know that the expected value is 50. But notice a few things about this. It's the expected value, but you don't actually expect to get 50. You don't expect exactly 50, but somehow you expect to be around there somehow. You expect on average to get about 50 heads to come up if you toss 100 times. So the expected value is not the same thing as the most likely outcome, or even the thing that is likely to happen. Instead, it's telling us something about of all of the possible things. When you look at all of the things that could happen, on average, you expect this thing to happen. So in fact, sometimes the expected value is not even a possible outcome. It's often completely impossible to hit the expected value, as we'll see in a couple of examples coming up. So it's not the thing that you expect to happen, but somehow it gives you a rough idea of the range of expectations that you might have over the time. And so it's a kind of average. The formula for this, so the formal way that we actually calculate the expected value is as follows. You take every possible outcome that could happen from your process. So for example, in the coin flipping that we just talked about, you could get anything from 0 to 100 heads coming up. So that's 101 different possible outcomes. Each of those outcomes you multiply by the probability that it will happen. So you would take your 0 heads times whatever the probability of 0 heads is, and 50 heads and times the probability that you get 50, and 43 times the probability that you get 43 heads. And so you take all of those little products and you add them up. And when you add them up, that will give you the expected value. So basically what we're doing is we're taking all of the possible outcomes, and instead of just averaging them, we're taking a weighted average, where the weights are determined by how likely that outcome is. So we'll do a couple examples now. Let's say we did a single coin flip. What's the expected value? We're counting the number of heads again. So if a head comes up, then we get 1 head, and then we multiply that by 1/2. 1/2 being the probability that the head comes up. If a tail comes up, then we have 1/2 times 0, right? 0 heads times the probability 1/2 that would be the thing that happens. We add those together and we get 1/2. So the expected value, the expected number of heads from one toss is 1/2. Now, of course, you recognize that you can't actually toss 1/2 head, but somehow this gives us an idea of something. It tells us something. That 1/2 sits between the 1 and the 0, and where it sits tells you what you expect to happen in the long run if you repeat this a bunch of times. So let's think about a slightly different situation. Suppose that instead of tossing a coin, I'm rolling a die, a 6-sided fair die. What's the expected value of the number that will show on the die when I roll it? The expected value turns out to be 3.5. Again, not something that you can get when you roll a 6-sided die. So to see how this is, we reason as follows. Since it's a fair die, we expect each side to come up equally often, or about 1/6 of the time. So the expected value will be, well, we get a 1/6 of the time. we get a 2 1/6 of the time, a 3 1/6 of the time, a 4 1/6 of the time, a 5 1/6 of the time, and a 6 1/6 of the time. If you multiply those together, add them all up, you get 21/6, which is exactly 3.5. Right? You can think about the values 1 through 6 that could come up on the die, and laying them all out. Somewhere in the middle of those is that 3.5. Right? And that's the expected value. If you did the roll 10 times, then you would expect about 3.5 each time. Overall, you would expect about 35. And that actually brings us to one of the important properties of the expected value, which is additivity. One of the nice properties is that it is additive, meaning that the expected value of A plus B is the same as the expected value of A plus the expected value of B. Now, I know that sounds pretty abstract. There's a little formula encapsulating that. But let's go back to our example of flipping a coin 100 times and see how it applies. What are we saying here? Well, each individual flip, we figured out, has an expected value of 1/2 head. So to get the expected value of 100 flips, we just add up the expected values of each individual one. Right? So the first flip has an expected value of 1/2, the second 1/2, third 1/2. We add that up for all of the 100 flips. So 100 times, we're adding up 1/2. So that's 1/2 times 100, which is 50, which we already said is the expected value. So you see how it kind of goes together. This is often a very useful tool because you can break down expected values for complicated events by separating them into simpler events that are independent of each other. Now, all of the examples we've seen so far, each possible outcome has been equally likely. Let's take a look at a more involved example where the likelihoods of the outcomes are not the same. So, let's take the example of insurance. Suppose that you plan to buy a new laptop for $2,000. And when you do that purchase, you are offered a simple form of insurance, like an extended warranty, for $25. Compared to the $2,000, maybe it doesn't seem so bad. What it'll do is it'll cover you if the screen gets damaged, or if the hard drive fails, or if the power supply needs to be replaced. What is the expected value of this insurance policy? Would you buy it for $25? Well, the answer to this depends on a few things. Basically, for each of these things that can happen that the insurance covers, how much monetary value do you get out of that? How much would you have to pay if you didn't have the insurance? And then, importantly, going along with that is how likely is each one of those events to come up? So let's say that the probabilities are the ones that I've put in this table here. Now, these are all totally made up, but maybe they're reasonable. So let's say that the probability of screen damage is about 1%. Like that you're going to really seriously damage your screen at some point in the first couple of years of owning it. Is going to be a 1% chance. And let's say that repairing that screen would normally cost $400. Okay, the hard drive failure happens about 1/1000th of the time, right? So a 0.1% chance that the hard drive is going to fail within those years. Replacing that hard drive is going to cost you $1,000. And then finally, the power supply might fail. We'll say happens about 1 time in 1,000 also, but the repair cost for that is only $100. So how do we figure out the expected value? Well, there's another possible outcome, which is that none of these things happen. And we can figure out that probability by just taking 1 or 100% and subtracting the probabilities of the other three things. And that leaves us with 988 over 1,000. In that case, the insurance is worth nothing. You get $0 return out of it then. Okay, so what is the expected value of the insurance policy? Well, we take each of these things that could happen. It could be a $400 repair, a $1,000 repair, a $100 repair, or nothing, right? And then we multiply by the associated probability, and then we add them up. So 400 times 1 over, right? So 400 times 1 over 100, 1,000 times 1 over 1,000, 100 times 1 over 1,000, and 0 times 988 over 1,000. If we put all that together, it comes out to 5.1. So the expected value of this warranty, this insurance policy, is $5.10. Would you pay $25 for it? Maybe you would. Maybe you know that in the future you aren't going to be able to afford $1,000 and you want to hedge your bets. So the expected value doesn't tell us everything. It doesn't tell us nearly everything. There are other reasons why you might make a decision. But on a pure monetary value of how much you think this thing is going to be worth, this warranty, you would expect that if it happened, if you had many chances, or if they sold many of these things, they would on average pay out about $5.10 to each policyholder, while asking for $25 for that policy. That's a pretty profitable business. So think about this the next time you're offered a extended service plan on something that you purchase. Maybe even if it's not that big of amount of money, maybe it's still a waste. It's not entirely clear, but also it's not entirely clear that this is the only number you should think about. All right. So one other example, we'll take a look at the lottery. This was also a topic in the reading. So lottery makes a lot of very extreme examples, but I picked one that's like pretty mundane, not too crazy. This is a real prize pool, a real game that exists in the New York State Lottery. It's called Winnings. And I've listed here all of the different prize amounts that are involved with this thing. You can win $1 million on this scratch-off ticket. That's pretty great. You can win 5,000, 400, 200, 150, 30, 20, 15, 10, 5. I'd take any of those right now. That sounds pretty good. And then we know the associated odds. So the lottery is required by law, of course, to publish the odds of winning the prize. With that information, we can figure out the expected value of this game. So $1 million times this odds, $5,000 times these odds, so it would be $1 million times 1 over 2.5 million, 5,000 times 1 over 692,000, 400 times 1 over 41,200, and so on down the line, and you add them up. And if you do all of that, you get an expected value of $3.27. Fine, no problem there. How much do you think this ticket costs? Well, it's going to be more than $3.27. It turns out that this particular scratch-off ticket costs $5, right? Which makes, you can kind of see that. There's your $5. That's just getting your money back. So if you bought a bunch of these tickets, right, the expected value each time is $3.27, but also each time you have to pay $5. So in the long run, what you expect to do is, on average, you lose $1.73 every time you play this game. That's it. I mean, really, you mostly lose $5 every time you play this game. But on average, it averages out to about a loss of $1.73 per game. So again, this is something you can see that difference and decide whether it's worth it to you to go ahead and play the game anyway for entertainment value or for some other reason. But there are other ways of looking at this, right? Again, the expected value doesn't tell you everything that might be important for you for making this decision. So one way you might think about it is that, well, there's an 11% chance that you'll break even, right? That would be this thing here, the 1 in 9.09. There's a 13% chance that you will make some money, right? That's everything from here on up. If you add up all of those percentages, you get to 13% chance of winning some money. And that leaves a 76% chance that you will lose money, that you will lose your $5, and that's the end of it. So there's some other ways of looking at this, but the expected value encapsulates something important about the way random processes work, and it gives us a way of taking all of this information, right? Like looking at this table, right, with all of this different information, it's hard to make a decision on that basis. Is this a good bet, a bad bet? Is it, am I going to lose my money quick, or am I going to lose my money slow playing this lottery? Having this single number of the expected value is very useful for trying to kind of clarify what it is that we're getting ourselves into in situations like this. It doesn't tell the whole story, but there's information in there that's useful to think about. So again, expected value is a weighted average taken over all of the possible outcomes of a random process, and the weights that are given